Okay, good afternoon, everyone. So my name is Massimo Gurioli, and as the head of the university degree in optics and optometry, we are organizing this series of scientific and didactic knowledge and tutorial webinars. So as you can see, we have scheduled a few of them. Today we have Thomas speaking on metal lenses, and then we have several others going from design to technology and to surgery, etc., etc. So for the non-Italian speaker in the audience, I have to say that most of them will be in Italian. I'm sorry, but that's what we do. So I want, before going to the seminar today, I want also to advertise you the next one. The next one is on light and colors, and is an history of our understanding of colors from very past, let's say Aristotle, down to Maxwell and other important physicists that eventually understand how our vision and color is related to the anatomy of our eye. Today we have a quite interesting seminar on metal lenses by nanophotonics. I will leave Thomas to explain what this means. And I want to say that Thomas Krause is a professor at the University of York. He has a big group in photonics, which is a science to try to use and exploit light to do some applications. And he is very active in many different directions, including quantum sensoristics, telecommunication, and also optical tools all today. And before giving the speech to Thomas, I want to explain the rules. So you in the YouTube, you have a chat where you can put your questions or comments or whatever you like to do. And I will read these comments to Thomas and he will reply. And Thomas will stop after 20 minutes, more or less, for any question or comments. And at the end, there will be plenty of time for discussions. Plus, we have a panel of experts that at the end can show up in video and audio and ask questions and make comments. So I'm very happy to acknowledge these friends and distinguished scientists like Mario Aggio from the University of Siegen, Lucio Andreani from the University of Pavia, Laurent Vivian for the University of Paris Sud, Lorenzo Pavesi from Trento, and Nick Vanus from IFCO Barcelona. So with this, I more or less close my presentation, and please, Thomas, go ahead.
Okay, so thank you for the lovely introduction. I think it is an excellent initiative, and I'm pleased to be part of it, although I'd much rather be with you in Italy just now and have the live experience, but we make the most of what we can. So at least there's little overhead in participating. So I also welcome the other participants outside who I cannot see, but I hope you gain a little bit of insight and you learn something today. So my topic is metal lenses, and these are made by using nanophotonic tools. In particular, you can see in the center, can you see my arrow? Maybe not.
Maybe not.
Maybe not. Well, we'll just have to leave. Well, in the center, you see a small nanophotonic structure. So here, this whole window is maybe 3 by 4 microns, to give you an idea. So this is all very small. So we're structuring material on a wavelength scale, or in fact on a sub-wavelength scale. So these structures are smaller than the wavelength of light that we're using. And we're doing all of this in silicon. And I explain why and how and all the rest of it. Now, this is a very fruitful collaboration between a group in Sao Paulo led by Emiliano Martin, who is a former student of mine, and also Juntao Li at Sun Yat-sen in China, who's another former student of mine. So it's always interesting to have calls between them. So we spun the entire world, and I think that's very exciting. So they all made major contribution to this work. So I'd like to acknowledge them. Okay, so all these pictures I'll explain, so let's move on. So what's the point? The point is we want to make lenses, and I show a lens on the left, and we all know what a lens looks like, and you know it. The light comes in and it refracts at the surface and it forms an image. We all know this. So why would we want to replace it? Well, you can see the lens I've drawn there is rather fat. So in many instances, you don't want a fat lens. The fat lens gets in the way, particularly if you think about miniaturized systems. For example, in your mobile phone, the camera in your mobile phone, and here I show mine. This is where's a pic? You can just about see there's a camera there. I've got two. This is the first model that had two cameras. This camera has got 5 or 6 lenses in it already, and you know how small the mobile phone is. So this is really it's not micro optics, but it's very small optics. So if you could make this with flat lenses, that would be already a big improvement, and it would allow you to improve the packing density and make the whole packaging much simpler. So the mobile phone companies are definitely very interested in this field. But then if you look at the picture on the right, this sort of thing that looks like a hat or a mountain or something, this is just an arbitrary phase distribution. So you could grind glass like this, say you could do this, and it would do something special. I don't know what it would do, but that's not the point. The point is, we don't just want to do planar lenses. We don't just want to do curved lenses. We want to do arbitrary phase distributions. And why this is interesting, I'll come to. So in terms of interest here, there's 2 reasons we want to do this. We want to replace bulk optics, as I say, but we also want to do something new, something you cannot do with glass lenses. And obviously, as researchers, this is more interesting for us. But let's start with replacing the bulk optics. And this has led to this idea that, of these tiny lenses, people think about medical devices, for example, including this in an endoscope. And the wise people in Davos at the World Economic Forum, they voted, and then they voted for these tiny lenses as one of the 3 top 10 emerging technologies in 2019. So that gave it a huge boost, and that gave a lot of commercial interest. And in fact, the first company is already formed. It's called Metalens with a Z at the end. And they make these nanostructures, and they're mainly targeting, for the moment, the machine vision. So not for smartphone cameras, but for cameras in automation in machines, again, to make things smaller, simpler, lighter, easier. Okay, so there's clearly a big driver. Now, let's start with the science and how all this works. And we recently published a review paper that came out in December last year, so about a year ago, where we explained some basic principles. So if you want to learn more about it, there's a good resource for you. And I've structured the talk in 2 sections. One where I talk about on-axis. So you think about the paraxial photonics, where you're on the optical axis. And then the second part is off-axis, which is in fact what we're trying to emphasize in this picture on the front page. Now, as I said, when you do this, you want to create an arbitrary phase distribution. So you need a very thin film to control phase. In this picture, I've got this mountain on the right where you have the arbitrary phase provided by the different thickness of glass. Now, as I said, we don't want to do this. We want a planar structure. So we need to control the phase in another way. And that's the point of the next slide. What can we do? So there's a number of things. You make these nanostructures, as you saw in my introductory slide, and you create a resonance. As we know, if you have a resonance structure, the light oscillates and creates a phase delay by multiply passing the structure. So on the left-hand side, you have this idea of a localized resonance. So you imagine these little circles that I show, they can support resonances. So the light enters the circle, resonates around, and leaves again, and that causes a phase delay. You can also have an extended resonance. So I show this sort of 2-dimensional grating type. It's the same idea. The light enters, resonates, and that's how you generate a phase delay. Then you can also have a effective index where you make structures of where you basically vary the amount of refractive index material in the optical path, and that gives the phase delay. And the last one, the unpronounceable Pancharatnam Berry phase, or in short PB phase, you inflict a phase delay on circular polarized light simply by having this rectangular element and you rotate it in, but you need circular polarized light. But this is in fact one of the most elegant ways of doing it, except you need to condition your beam. But nevertheless, so you can see there's a number of ways of doing this. Now, this whole field was really invented by the plasmonics community. So this is people making these sort of nanostructures in metals. And here I show a little gallery of beautiful pictures, and they really thought about how to control phase with these resonances, and they brought loads of interesting results. The catch is these plasmonic structures, they all exhibit a loss. And if you want, particularly if we want to work in transmission, as we would like to do for a mobile phone or other imaging applications, then you don't want to lose half your light or more to metallic losses. So that sort of, it's gone away now, but I still think there was a lot of inspiration came from this community. So instead, what we're doing, but we started with this sort of structure, which is a guided mode resonance. So this is one of those extended resonances I talked about. So we started this sort of thing about 10 years ago, and the basic idea is it's a second order grating. So it's like the same as in a grating coupler for a waveguide. You shine the light from the top, it couples in, and then gets Bragg reflected inside the structure, and depending on the phase between the incoming light and the outgoing light, you then reflect or you can transmit. So it's an interference which is determined both by the Bragg mirror that you formed, but also by the planar interface between the top and the bottom of this structured surface. So that's why we often call it a Fano resonance. Fano resonance being the interference between two types of interference phenomena. So here it's the Bragg resonance and then the thin film interference of this guiding film. Okay, so this allows us to control phase. And now if you want to make a lens, it's quite simple. You change the structure, and that allows you to control the phase. And then I show a phase front. And in fact, I need to recognize Fatal, who worked at HP about 10 years ago, and they first came up with this, and we took it a little further. So the Clem Optics letter is our first paper on these types of meta lenses. And we didn't call it meta lenses then. We called it high contrast gratings, but the physics is the same. So there is one of these, and you can see it looks quite pretty. At least I think it's pretty. And you basically have this variation of the grating, which gives you the variation in phase, and clearly it follows the sort of a Fresnel lens type approach. If you look at the picture on the top, it looks like a Fresnel lens with these rings, where then you have a 2π phase jump. And so you're asking yourself, so why does he do all this stuff with the gratings in the center? Why don't he just do rings like in a Fresnel lens? And the answer is, this structure can control the phase everywhere. So whereas a Fresnel lens with rings can only controls it at every 2π phase step. So this efficiency here, as we then showed, we could reach 80% efficiency with this lens. And that was already at the time a lot better than I mentioned the plasmonic lenses. But this lens was designed to work in reflection. But yeah, it worked very well. So then we thought, I mentioned, what can we do with this lens that's a bit different? And this is a point I made in the introduction, that I don't just want to copy a lens. I want to make a lens that can do something that a glass lens cannot do. And here's a good example. We included this lens into a microfluidic channel. And with my colleague Kishan Dalakia in St. Andrews, we did some optical trapping. And you can see these beads in the video on the right, how they're trapped, and then sometimes they get a little kick and they lose them. They come out of the trap, and then a new bead comes in. So here we've shown that you can use this type of lens as an optical trap in a very thin microfluidic channel. So that's a nice example for something you couldn't do otherwise. Okay. So then in 2016, Capasso's group published this science paper, and this was really the first time that the wider community took note. So first of all, this was the first big paper that talks about metalenses. As I said, we hadn't used that term. And it also made the connection to the mobile phone, which hadn't been done before. And it also introduced this Pancharatnam berry phase that I talked about earlier. And they explained, they showed very nice high efficiencies, and they showed some beautiful pictures here. I show higher order angular momentum, optical angular momentum. So this really was quite a breakthrough that I think, which is the basis for this World Economic Forum vote as well. So Capasso has been driving this field for some time. So that gets a lot of credit. However, if you look back, you will find a very similar idea was published almost 20 years before, in the late 90s, by Philippe Lalanne. And he had already realized this idea of phase control using titanium dioxide structures, which is the same that Capasso uses. And he also recognized, he realized very high absolute efficiency, and both of these structures in the 80%. So some people say, well, Capasso just stole the idea, but I would argue all of us should sometimes look back at history, and then maybe it's useful to reconsider certain things, because Lalanne certainly did not think about applications in mobile phones, and all the other wider view on meta lenses that Capasso clearly initiated. So an interesting view on history. Okay, so then in comes our work. So we then started calling this thing meta lens as well. And we didn't want to use titanium dioxide because, well, we didn't have the manufacturing capability for titanium dioxide, and we also like silicon. And I also believe if you want to do anything on a large scale, if you want to do this mass manufacturing, and I tell you, this mobile phone camera, the camera itself cannot cost more than $1 or $2. So if this meta surface is expensive to make, it will never make it into this camera. So we need to make this at very low cost if we want to be competitive. And I would argue silicon, planar silicon, is really one of the very few routes you can take if you want to do that. So we like silicon. We've done a lot of work in silicon. So we said, well, let's see whether silicon can work here. Now, you notice the beam I'm using is green. Now, what's the problem with green and silicon? Well, here's the absorption of silicon. And if you can't read the numbers, I'll zoom in a second. But we all know silicon in the visible is terrible. We use it for solar cells because silicon absorbs light in the visible very well. And here's a zoom in, and sort of if you go to 500 nanometers, so between 500 and 600 nanometers in the green, the absorption coefficient of silicon is 10 to the 4 per centimeter. That's a huge number. Now, if you think how big, go back to this slide. Now, the path length here, and this is an effective index type approach, the path length is about 250 nanometers. I'll go back to here. So 10 to the 4 per centimeter, that means 4 orders of magnitude less. 10 to the 0 per micron, that means, so 1 per micron. So e to the minus 1 is your transmission. And then if it goes to 250 nanometers of silicon, actually, it's only e to the minus a quarter, which isn't very much. And then also, you look at this, and you think, well, actually, half of the material is etched away. So now we're talking e to the minus an eighth, which is about, 80-something%. So the loss starts to become very small. So actually, it's not such a bad idea to do this in silicon. And here's then our example. So we made this and we measured 67% in experiment, 71 in theory. And again, half of the difference between those 67% and the 100% you would really like is absorption loss. The other half is scattering. And as I mentioned, the titanium dioxide gets to about 80%. So we're not very far away from the titanium dioxide. And it gets better. So then we thought, okay, Capasso does these wonderful, let me call it PB phase, it's easier to say. We can do this as well. And now here's the next bit. If you do high numerical aperture, and all of us who do microscopy know, for really high numerical aperture, you need to do immersion lenses. And immersion means you pour oil onto your structure. Now, if you do this with titanium dioxide, you lose half of your index contrast. The lens doesn't really work very well anymore. But with silicon, because the index is about 4, whether the background is 1 or 1.5 for oil doesn't really matter. So here, that's what we use then to show a very high numerical aperture, which you could not do with a titanium dioxide metasurface. So there's a clear advantage of using the high refractive index of silicon and tolerating the little bit of additional loss that you get. Okay, and here's an example here. We really 200 nanometer spot size. And as I said, you cannot do this with the titanium dioxide lens. Okay, so this is, I'll come to my first break. So I've told you about how to make a meta lens in a high index silicon structure. There's a variety of ways of doing the phase delay, and I've demonstrated to you we can do both high efficiency and we can do high numerical aperture. And as a little gimmick, I showed you our lens, use it for trapping. And that's a nice example for where you do not want to use a thick glass lens because it would get in the way of your channel. Okay, let's have a pause here.
Yes, so thanks, Thomas, so far. And anyone can ask a question, make a comment. As I used to say, there are no stupid questions. So if you have anything you do not do you not know and you didn't understand, please ask. So you can write in the comments and I will read the question to Thomas. So everything very clear, Thomas? I don't know.
Yeah.
Let's see.
Either nothing understood or everything understood. Let's assume the latter.
Let's assume the latter. And yes, I think, I mean, it's a nice presentation. Maybe you can, do you have a slide on Fresnel lens, the old one, just to, because I'm not sure that the students in the optics, maybe at the end, maybe you can show the difference from a real Fresnel.
Yes, okay, let's come. Yeah, I definitely have that.
The old type of Fresnel lens at the end, and you will show. Maybe that will try to explain this control of phase. I saw one seminar of your, you did this and was very, very didactic.
Okay.
I think you have some aware.
Yes, I do. Okay.
Okay, so now this bit of also pause. There are no questions, no comments, so please go ahead. Okay.
So the second part, as I said, we now want to look off axis. This little picture makes the point. And why is off axis important? Well, you see, everybody who makes a meta lens uses a laser beam and focuses it down. And that's actually quite easy. What is much more difficult when you want to take an image, you need to take rays that are off axis. So any lens that does imaging uses off axis rays. So it's very important. Now, what's the problem? Well, the main problem I will talk about is called Coma, which you do get in a normal spherical lens. And it looks like this. It looks like a comet. It looks like the tail of a comet with a bright head. And that's why it's called Coma. And it's because not all the rays are focused at the same distance. So there's this overlap, and that well, it's relatively easy. This is very fundamental optics. Now, why does this happen? First of all, let's look at what it actually looks like. This is a picture of the normal resolution target taken with the type of lens that Capasso designs. Now, of course, they don't show this picture. They will only show you the very center. They will not show you the full field of view because it looks pretty horrible, right? So this is a problem we're trying to solve. So let's but first understand the problem a bit better. So here is, I just use as a simple explanation, a parabolic mirror, which is a focusing mirror. And you have three sources, Q1 to 3, and they all end in a focal point. That's great. Now, when you tilt this system, so I've tilted the whole system except for my sources, and you notice the Q1 and Q2 look okay, but Q3, there's something gone wrong. It reflects behind the mirror, which is clearly not possible. So what really happens is this. So the outer ray doesn't go into the focal point. So this is a very sort of Mickey Mouse explanation of this Coma effect. This is the same idea, right? So the outer rays, they don't quite behave as you want them to, and that gives you this Coma effect. Okay. And as I said, this happens with the hyperbolic. They call it the hyperbolic phase, and I'll explain more about this. And if I look on the top plot, you see for normal incidents, it works beautifully. But for incidents as little as 15 degrees, it does not. You see the focal point becomes an arc, and it becomes a mess. So what can we do? Well, first of all, what other people have done, they've thought about this and thought, well, we need to correct the light. And on the left, I show some work from Caltech, from Andre Faron's group, and they basically took a thin film and patterned it on both sides. So you have a corrector on the top and then a focusing element on the bottom, and that indeed works. But you notice they already had to include a stop. So they have to include an aperture, which limits the effective aperture you can achieve. And on the right is a very recent paper from MIT, and they basically do the same. They don't do the correcting metasurface because they realize you don't actually need it. All you need is a stop, so an aperture at some distance away from the meta lens, and then you can also correct for this Coma effect and achieve a wide field of view. But as you notice, the ray picture on the right tells you that you only use a limited fraction of the metasurface. So you really reduce light throughput, and that clearly is not desirable. It works, but it severely uses throughput, and it's much more complicated, having to work on two surfaces. So we wanted to see whether we can do all this on one surface. So we went back, we thought about it, and we like kspace. Now, kspace is a bit more advanced, so maybe the next few slides, not everybody will follow, but the experts will clearly appreciate this. So what actually happens, if you think about this, so the light comes from the bottom. Imagine a ray of light, light beam comes from the bottom and gets focused. Now, what the metasurface really does, it gives you a radial K vector. So the light gets deflected towards the inside, and that then forms a focal point. So we think about this as adding a K vector to the incoming light. And that's what the metasurface does, right? So if I take the same picture, and now what gives me the sharpness? The sharpness of the picture is actually provided by the outer rays. So if we have a stronger component from the outside, and I'm showing this with these fatter rays, that means we get even better focusing. And that's exactly what the hyperbolic profile does. That's why it performs so well on axis. So you get strong components from the outside, and they really give you very nice, beautiful, tight focusing. Now, what's the problem? Problem is this. Oh no, I'm just drawing, problem comes on the next slide. I'm just drawing this in this sort of strength of k vector graph. So I've got the k vectors, and I'm saying the outside k vectors are stronger than the inside ones. And I'm just drawing this as a parabola here. Now, now is the problem? If I now come in at an angle, I basically shift the entire plot in k-space. So because the incoming light already has a radial k component, so I'm now distorting this. And now I achieve an unbalance. So the rays on the left and the rays on the right are no longer symmetric. So that gives me a distortion. And that's the problem. Right? So here I'm showing this. This is a real calculation. The hyperbolic phase, when it's in the center, is beautiful. It gives you this red distribution in k-space. But if you go off axis, then you shift the distribution laterally and you cause an asymmetry, which gives you this sort of distortion that I showed earlier, and that leads to the coma. So we don't want this. What do? Well, we revisited the spherical lens and looked at it in the same way. And if you draw the k-space for the spherical lens, it looks as I show there. So it's much flatter. So if you imagine you're shifting this distribution, the asymmetry you produce is much smaller, which already just from looking at this tells you that the spherical lens is more tolerant to angular changes than this hyperbolic lens. So that's a good idea. But you also see it's not perfect, there's still rays going astray and it's not ideal. So my question is, can we use the spherical lens as a basis for improving this scenario? And can we make a better spherical lens using the meta surface paradigm? And here's the answer. This is the most important slide of the talk. So we thought about this, and we thought, in this picture, I'm showing you a very fat spherical lens, and we all know that the lens has glass, and we can have maybe a refractive index of glass is 1.5, maybe we can go up to 1.8, but that's about it. So normally we control lenses via the radius because we don't have much room to play on refractive index. All the materials we use are between around 1.5. Now, if we design a meta lens, we do not have this limitation. We can design a phase profile which can mimic any radius or any index, and that's exactly what we've done here. And that's why we call it the impossible lens. So what we've done, we've increased the radius and increased the index. And because we're not constrained by having to use glass as an optical material, we can artificially mimic any index or any radius. So we can make this a flat lens of infinite refractive index. Now, clearly, we can't make this, but we can use the equivalent phase profile that this lens would produce and replicate it in the meta lens. So that's how you have to think about it. So we're creating a phase profile here for a lens with infinite radius and infinite index. And if you do that, you notice my k-space distribution becomes much flatter. So if I shift this around, it's already much better because it's almost translation invariant. You notice there's still a catch. You're losing a bit of k-space on the left-hand side, but I'll come to that. But the first observation you note, if I do this impossible lens, my k-space distribution becomes very flat. So that makes it useful for angular incidence. And I'll develop this more. Okay, so that's a key bit. So we're mimicking a phase distribution for infinite radius and infinite refractive index. Okay, and now does it work? Well, it's quite remarkable. You notice here, so the hyperbolic lens, as I showed you several times now, it has this distortion for angular incidence. The impossible lens doesn't do it. The impossible lens generates a very nice focal spot irrespective of input angle. And you notice, so the plots on the right, on the bottom right, is the focal point for different input angles, and it doesn't change. It's always the same. So this is really nice. It works really well. The more observant people may realize there's a catch here, and I'll come to the catch. What's the catch? Well, actually, I'm gonna go back to this slide. I've now added these red boxes on the bottom. Now, what's the problem? The problem is, so the red box on the left, this is where I've lost k vectors. So these k vectors no longer contribute to the image, and the red box on the right, so the k, this is k over k naught, so the k is now larger than k naught, which means I have an imaginary k vector which can't propagate, so that light also gets reflected. So effectively what I'm doing, I'm reducing the effective aperture of my lens. And you can see this in the picture C. The effective aperture that contributes to the image is smaller than the size of the lens. You notice on the bottom of this lens, the light doesn't start at the edge of the lens, it starts a bit higher. That's exactly because I've shifted it out of the real space. It's imaginary there, and it doesn't contribute to imaging. Okay, so can we improve this? First of all, does it work? So my group is really, our key technology is electron beam lithography. We make these nanostructures. We love making nanostructures. And here, this is really hard work from two of my students. And you notice, so they've made these lovely little arrays of pillars. And this is really very difficult. So it's 190 nanometer period, and we have to control the radius of these pillars. And this structure is not polarization sensitive. So we're not using the PB phase because we wanted to do something that was polarization insensitive. And this is what we have achieved. And it works. So here's a 2 millimeter lens, and we mounted it into a camera, and we got a nice picture. Here's a picture. So the picture on the left is the Metalens, our wide field of view Metalens, using this impossible, this R and N to infinity. And the picture on the right is the equivalent hyperbolic lens, which I've already showed you. And you can see it's quite amazing. You have definition all the way to the corners. Now you may say, well, this is distorted. This is a fisheye effect. That's only because we're using such high magnification. So it's such a small system, and you could easily correct for this. But the key point is you have high definition all the way to the corners. And in fact, we demonstrated the point spread function. So, you know, the sharpness of the point is basically unperturbed up to 89 degrees. That's the biggest angle we could measure. So it really works. That is the key message. Now, there's another example. So here's the impossible on the left and the hyperbolic on the right with the university logos. And I just want to point out the picture on the bottom right shows you the hyperbolic is slightly better in the center of the image, as you would expect, but clearly at the edge, the impossible is miles better. Now, let's come back to this question with these red boxes. So can I avoid these red boxes? Can I make sure that this meta lens has always got real K components? And the answer is yes and no. So the red box on the left, where I lose my K components, that I can fix. The red box on the right, where some of the K components become imaginary, that I cannot fix. But at least I can fix something. And how do I do it? Well, I increase the numerical aperture of my impossible lens. So if you increase the numerical aperture of the impossible lens, your K distribution becomes wider. And that's shown, it's a bit small, but the top left picture shows this. So this is now a picture for various numerical apertures. And you see the blue one is roughly what we looked at before. But now if I increase the numerical aperture to 0.9, which is not particularly difficult, I can make the numerical aperture, this K space much wider. So if I now shift it, it's always flat. So I don't lose my K elements anymore. Now, the price I pay, I only use a part of the lens. So you now have to, this requires a bit of imagination. So if I say, you know, look at KR goes from -10, from -2 to +2, this means even for normally incident light, about half of the lens does not contribute to imaging, because even for normal incidents, the K vectors smaller than -1 or larger than 1 are imaginary, so they do not contribute. So that's the price I pay. But when I take the angle, because the K-space is so flat, I pay no penalty. And before I go to the bottom picture, this is indifferent. Let me just illustrate this a little better. It's already there, it is again. So this picture I showed you earlier, and you notice the beams on the bottom do not use the full extent of the lens. This particular lens extends from -20 to +20, as you can see on the top left. So the physical size of the lens is 40 microns in diameter. But the impossible lens on the bottom only uses half of this. So the space between 10 and 20, or between -20 and -10 on the bottom left, this is all light that is lost because the K vectors that are generated there are imaginary. So they cannot contribute to imaging. So that's the catch. You pay for this wonderful large field of view with a reduction in the effective numerical aperture. So in a way, it's similar to these compound lenses I talked about earlier, but I would argue this is much more elegant here. And in fact, we don't lose as much, but we lose something. So it's always important to make sure that you're honest about the trade-offs you're making. So, and this is illustrated here. Go back to this slide. If you look at the resolution, and this is a picture C, so the full width half max for the black curve goes down with numerical aperture. This is a normal lens, which is what we would expect. So the higher the numerical aperture, the better the spatial resolution, the smaller the spot. But you notice for the blue and the red lens, let's look at the red lens. The red lens was the one with numerical aperture of 0.9, and it stops at about 4, so that the focal spot is about 4 wavelengths in size, and it stops there irrespective of numerical aperture. But it's equivalent to a lens with a numerical aperture of 0.3, and in fact 0.3 is the numerical aperture on your mobile phone camera, on the very best mobile phone cameras. It's about 0.3. So actually it's not a problem for practical application. Most practical lenses don't use a higher NA than 0.3, but with this technology you get the NA of 0.3 and you get the wide field of view, which you do not get with other types of meta lenses. So I think it's a trade-off worth making, but clearly you need to be aware of it. Okay, so that's the number one. Then final question I often get asked, so your lens is very small, why does it not work? Could I not just use a pinhole camera? And this is not a nasty question, because if you look in the literature, I would argue a third or half the meta lenses you see, you could replace them with a pinhole that would work just as well. So many people often they show meta lenses with 50 or 100 micron radius, and you don't need you don't need all this stuff in the middle. You could just use a pinhole camera. And here I'm giving you the formula for a pinhole camera, 2 times square root f lambda. And if I put in our case, we use f of 750 micron, we use lambda of 550 nanometer. The diameter of the pinhole camera is about 50 microns. So if you make a meta lens of 50 or 100 microns, you might as well use a pinhole. But our meta lens is 2 millimeters. So clearly it's better than a pinhole. But we made the comparison because I was interested, and it's interesting. So on the top you see the meta lens, and we can get an image with a pinhole camera. That's on the bottom. And well, why do I not use a pinhole camera? Well, the argument is my meta lens, because it's so much bigger, catches a lot more light, so I can do a much shorter exposure time. If you know anything about pinhole cameras, because they use such a small hole, the flux of light is very low, so you need very long exposure times. But it works. So if exposure time is a penalty you can pay, then I would recommend you use a pinhole and not a meta lens. But most people, they don't want, they want to take dynamic pictures, so they want a short exposure time. But, and here's another but, Many of these meta lenses, they can do something very well, but they can't necessarily do everything. So this particular meta lens is very good at numerical aperture, field of view, but not chromatic. So the point here is, that it only works at one wavelength, or at a narrow wavelength range, whereas the pinhole is much better at achromatic transmission. So I just want to highlight this. You do not have a meta lens which does high numerical aperture, high field of view, and broadband operation. Does not exist. And in fact, I mentioned this as a challenge for future work that people may want to think about. Okay, so in conclusion, I've introduced our idea of a impossible meta lens where we're mimicking the phase distribution you would get if you could make a normal spherical lens of infinite radius and infinite refractive index. And what I explained to you, you pay for it with reduced spatial resolution because you don't use the full numerical aperture of the lens. That's the price you pay. But still, I think it's a very interesting approach. And I like the term impossible because you cannot do this in bulk optics, which brings me back to my initial motivation. I want to do meta lenses because they allow me to do something I cannot do otherwise. Okay, so that's my. I just have, if you're interested, well, I've got this slide again. For opportunities for future research. So I've just made the point about achromatic meta lenses. So I think it needs some clever new designs where we can overcome this limit, where we can have both high numerical aperture, high field of view, and achromatic operation. And also, we should think more about things we cannot do with normal optics. And polarization is certainly one thing. Polarization-dependent functions are difficult to do with classical elements. You need to use, birefringent materials, which are difficult, but it's easy to implement here, as, for example, shown with the PB phase profile. So I'll leave you with these thoughts, and I look forward to your questions.
Thank you, Thomas. Actually, very nice talk. Thanks. Actually, there have been some questions from the public chat during your stop, but there was some delay. I don't know why, so I missed them. So now I will ask them. I think they are not students. One is called Dario Gerace. Do you know him, maybe?
a junior undergraduate, I believe.
Anyway, Dario is asking if there are any other materials that would still be cost effective and do the same job, I think, with respect to silicon.
Well, people have done it in gallium nitride. That's not cheap. As I said, titanium dioxide. So capacitor uses quite a difficult process using atomic layer deposition. That's not cheap. I would stick my neck out and say no. I really believe if you can't do it in silicon, it'll never be scalable mass manufacturing technology because it has to be so cheap. Semiconductors you cannot make cheap enough. 3.5s or similar semiconductors. Yeah, that's my answer.
Now there is another, I guess it's not a student. I cannot read the name because it's in Cyrillic, so I guess it's a Russian guest. Anyway, I don't know if you can read it. So he's asking, are there ways to build lenses operating wide spectral range? I think you approach this problem, but anyway.
Yes, people have done this. And people have demonstrated achromatic operation with low numerical aperture. Yes, and what you do, you control the dispersion at the meta atom level. So you imagine that, the problem is dispersion. Yes, glass has dispersion, but these nanostructures have a high level of dispersion. So what you do, you design each meta atom to have the opposite dispersion, so that the dispersion at the nanostructure level is opposite to the dispersion you get from the large structure. But for that, you need higher resolution, and you cannot do this with high numerical aperture. But there are other ideas that people might want to explore. Yeah.
Just to give some number, your metal lenses have a broadband bandpass of what? You can do
10 nanometer. 10 nanometer. It's not that much.
Okay, now there is Xavier Letartre. It's probably a comment. You say the thickness of silicon is small, but if you use resonances, the absorption can be high.
Yes, that's a very good point. Yes, I agree with you. The point is, that's why we use the effective index approach for this, because it's a single pass device. If you do multi-pass resonances, then of course the absorption will also go up. I agree.
Yeah, I agree too.
Now, Laurent was asking, what about germanium, to my material question.
This is private chat, probably, so we have to wait. It's the rule. It's a private chat.
Okay.
First YouTube, and then the experts. Then Laurent will ask by himself later. But I have no much more comments or questions. This is Emmanuel that is simply saying nice talk, Thomas. Thanks. So this is for you. And I think if you have any other question from the public chat, please do it. In the meantime, probably we can give the speech to Laurent. Giovanna, please.
Thomas. Very nice talks, thanks. It's very amazing that to see what you do with the sub-wavelength nanostructuration. That's good. That if you increase the refractive index, that you can also have a good response, and then germanium is compatible with the silicon technology. That if you use germanium instead of silicon, that it should be better or not?
I don't know the absorption of germanium in the visible.
It's quite
my guess is it's higher.
Yeah, sure. Yes, it's much higher.
Yeah,
but
but the index is also higher. You're right. So I agree, it's worth looking at. But I think we're at the limit of absorption. You don't really want to have any higher absorption. That would be my answer.
Maybe that if Massimo agrees, that I can ask another question. That you show a very nice behavior with one lens or Metalens. Now we know that for smartphone, every kind of system, we have several lenses. And then can we imagine to put a stack of Metalenses?
Yes, but I think this is unavoidable. I think the answer to my question, how do you make an achromat, will require multiple lenses. But in fact, I still like the idea that you can do it all with clever design. I would love a design where you have everything combined in one surface. I think that's just an exciting challenge. And if you think about it, what is a lens? It's a linear system. So I think fundamentally, you should be able to combine all these effects in a single layer. But I'm not sure it can be done.
Okay.
Okay, Thomas, I have another question from the public chat. Is a very young student. The name is Philippe Lalande. Maybe you know him.
Another undergraduate.
So the comment is, if you use silicon resonance, not only absorption grows up, but also it does not work because of shadowing. Do you agree?
Well, I went to Philippe's talk. He gave a similar talk a few weeks ago, and he explained shadowing very well. I agree. Yeah, but we don't in these the effective index approach. I don't think we worry about shadowing.
Thomas, maybe you can explain us shadowing. What is shadowing? What does it mean?
Well, maybe I should use this as an opportunity to show a Fresnel lens.
Okay.
You asked me this before. Now let me see.
And then Giovanna, please give the word to Mario Adjo at the end of this.
What am I doing here? Wait, this is a different. There. What do you see? So, you see this slide, Fresnel lens?
Opportunities. We see opportunities. You have to do share.
No, I have to do something else.
Share a different slide.
Wait. Sorry, right. Right. Can you see that? Multi-beam interference?
Giovanna has to put the slide on.
Okay, it's not possible now. I can't see them.
Maybe you have to close the other one.
No, the other are closed. The other are closed.
Okay.
So, but I can't see now.
Wait. I need to show. No, it doesn't allow me. No, now I'm in the same
Okay. It doesn't matter. We probably.
Sorry, I can't do it.
Okay, Mario, please, Giovanna. And
well,
I would say,
let me. Okay, look, I can do it with my hands. So a Fresnel lens. Well, I draw it on a piece of paper. So a Fresnel lens has this sort of sawtooth profile. So you're basically compressing the curvature into steps. So it looks like this. Right on the bottom. So what you've done before, in a normal lens, you have this profile, right? And you're taking bits back that are a wavelength thick. That's what a Fresnel lens does. Now on the top, if I now have a beam, it comes from the top, it gets deflected, gets refracted towards the inside, and then it bounces off this vertical jump. And that's the shadowing that Philippe is talking about. Now, you do not have this if your structure is only less than a wavelength thick. Then you don't have this effect. So this is a shadowing, and you don't get it with an effective index meta lens.
okay. So, please, Mario.
Yes, thank you very much for this very nice overview on meta lenses, Thomas. I have two questions. So the first one, you talked about the Coma. So what about the other aberrations, like spherical aberration and so on? And the second question is about the possibility to use this technology for focusing ultra-short pulses. So you were mentioning that they have a lot of dispersion, but can you actually compensate for it? Thank you.
Well, I mean, the first question. So I know the answer. I've forgotten your question. I'm sorry. It just. What was the first question again?
The other spherical aberrations.
Other aberrations. So yes.
And so on.
So the impossible lens still has spherical aberrations, but they're just very small. I agree. They don't not totally go. That's partially why the focal spot is not as good as for the hyperbolic lens. Yep. I think that's that answer. Then short pulses. Well, indeed. Well, if you can control the dispersion, then as long as you can accommodate the bandwidth of your pulse, then I don't see why it shouldn't work.
Mario, it's okay?
Okay, thanks. Yes, thanks.
So, any other question from the experts? This is a comment of Philippe to all of us. Nice, Philippe. Thank you.
Hello.
And so Lucio, please. Yes. Lorenzo. Okay. Lucio. No, Lucio.
Yes, Thomas, thanks very much. Then my question is, do you have in mind a specific application and as a part of it, is there any real application that can work with such a narrowband Metalens?
Well, the real application is the one I showed on my third slide. What the company is doing, they're doing for machine vision. So you only need a black and white camera that works about 900 nanometers. It doesn't have to be broadband. But I'm not aware of a real application that actually works over the full visible spectrum. So I think that is a problem. Where we get, well, we're currently working. I'm trying to push the wavelength to shorter. We're now working in the UV, which is another challenge, and I want to build a fluorometer, and I want to exploit the dispersion, so I can use an LED source and a photodetector next to one another, so that the light from the LED is focused. So the focal point, I want to exploit the dispersion such that the focal point for the fluorescence excitation and the fluorescence emission is different. So here I'm not trying to avoid dispersion, but use it because of fluorescence application. I need to use two different wavelengths. That's what we're doing just now. And it's difficult, but well, you know, it wouldn't be interesting if it wasn't difficult.
So that, I mean, you might expect this question, but did you identify a killer application as yet for the metalenses in general? Or is there something which is already in the market or on the way to go to the market?
I think the point about polarization I made at the end is very interesting, that you can, I mean, the army is interested in this, that you can use polarization imaging to detect targets that you couldn't see otherwise through fog or stuff. So that's part of the argument that Capasso's made, and I think it's a good argument.
And are there some, I mean, are metalenses on the real in the market in some applications as far as you know?
Well, the people from Metalens, they say that they're starting to have contracts, but it's only just started last year. So, yeah, I was a meeting in Washington just before lockdown, and they were presenting, and it was interesting. It worked.
Okay, so thank you.
As a last question, perhaps this is a little bit more technical, but as a material, tantalum pentoxide, have you ever considered this? Because this has higher index than titanium oxide, fully transparent, already used in some applications.
Yeah, but it's not much higher index than titanium dioxide.
Not much higher, yes.
We thought about it, but we like silicon, so we don't have access. Well, yeah, I can buy tantalum pentoxide and we can learn how to etch it, but I go back to the original argument. I really think you want to be CMOS compatible and you want silicon technology, and as we showed, it works.
Okay, yes. Okay, thanks.
Thank you, Lucio, very much. So there is Lorenzo has a question or comment, please. Microphone, Lorenzo.
Hello, Thomas. Very nice person.
Hey, Lorenzo. Good to see you.
Yeah, I really like it. I have 2 or 3 questions. So the first one is about the CMOS compatibility that you are claiming of. Are you considering to grow your lens directly on top of the sensor, of the optical sensor? In this way, you can really gain and use the CMOS compatibility. Otherwise, I mean, you are only using the CMOS technology to produce your lens, but actually it's not really integrated in CMOS. So this is
let's do one after the other. Otherwise, so clearly integrating meta lenses into our sensing activity, it has crossed my mind. So I agree. you could then think about including detectors and lenses all on the same chip. Yeah, I think that's a nice approach.
This would be very interesting. So the second, related to this one, so you say that your PhD student did an heroic effort in order to grow this 2 millimeter wide metal lens. And initially you were saying that anything that could be really on the market should cost a few cents, or I mean, a couple of euros. And how you manage the two? I mean, how you actually could industrialize this metal lens if you use E-beam and then you have really to throw the single. Or
look, Lorenzo, when I started photonic crystal 25 years ago, people gave me the same question. Now we can make photonic crystal by deep UV easily.
Yeah, but deep UV, you think that you can go down to few euro cents for? Because I mean, so people say that CMOS is not expensive, but actually, if you have really to pay for the fabrication costs, so they are expensive, unless you have the huge market. But you were saying you are targeting army application, and army is not a huge market. I hope at least, because if it is
no, I absolutely agree with you. But again, if I mean, that's why Capasso is pushing the smartphone market. And well, for example, even if you can't solve the achromat, I would argue, I've already got 2 cameras on this thing. You could have 3 cameras, one for RG and B. Separate the wavelengths. That would be a simple solution. You just multiplex.
This is very good.
And then you make 3 lenses, and making 3 lenses costs the same as making 1.
Yeah, this is very good idea. I do agree with you. Even better, because then you can really process the image and then you can really do very good work. So the last question is the following one. So you know that our eyes is using a lens, and you accommodate the focal length in order to make the image. So you do not, this is very different from what happens in the camera. Are you ever consider to look for a system that is able to change the focal length, so to accommodate the focal length of the lens by keeping fixed?
Yeah, well,
for example,
people are thinking about it. I mean, people are talking about using epsilon near zero materials, and then changing the index electro-optically. So there have been all sorts of proposals. I'm not convinced, but that doesn't mean there might not be a surprise. But I think that'll be difficult, because we all know, we've all done electro-optic modulation for a long time, and it's difficult to get big phase shifts with low voltages. And the optic, you're only passing through half a micron or so of material. I don't see this as a possible outcome.
But using piezoelectric material? No, don't know. I mean.
But they're not transparent. As I say, there may be surprises, but it's not. I don't think it's the obvious route to go.
Okay. Okay. That would really be a breakthrough. I mean.
That would be a breakthrough. Yeah.
Okay. Any case, thank you for a very nice talk. Yeah.
Okay, Thomas, I also have a simple question. I miss if you have any constraint on the focal length of your lenses. So they could be very small, I guess. You cannot have a lens of, let's say, 1 meter or 10 centimeter with this kind of system, or you can.
You can. But pointless. I mean, so I think if you want a lens with a large focal length, that means you're not.
I mean, yes.
Space. Use a glass lens.
Yeah. I mean,
There's no point doing all this for a large optical system.
I just want to know if you have any technical limits to this, because I mean,
because we can almost arbitrarily control the phase. So you can put as I said, infinite curvature. You can do very small curvature. You can do anything you like. That is easily designed.
Okay. Okay, so we have another expert that want to show up. So please put Dario on the video.
Hi, Thomas.
Hey, hey, Dario.
Hi, good to see you. I mean, this was just to say hello because you already been discussing a lot. My question on the material was more thinking in terms of plastic-like materials, let's say. So if you think about the usual lenses that we commonly employ, they are more or less some really cheap or plastic-like material. It might be expensive to process them, to nano fabricate them, but the material itself, it should be cheap, right? But maybe it's,
yeah, but you want the high index.
Yeah, exactly. So the problem is the high index.
But I mean, you can put silicon. We've done it. In fact, when we work with Lucio on solar cells, we put silicon onto flexible carriers. Silicon is very flexible if it's thin enough. So you could imagine a process where you can do that.
Anyway, Thomas, this smartphone we have already did very beautiful pictures. So, and I think the lens cost, I don't know, 1 cent. I don't know how much does it cost.
No. $2 or $3.
$2 or $3, okay.
It's not so much. But again, if you talk in billions and you can reduce the cost by $1, that's worth it.
Yeah, it's always the same.
But also, apparently, I'm told the thickness, even though this isn't very much, but the thickness is partially constrained by the camera and the lens.
I see. And
even if I look at my lens here, the lens sticks out.
Yeah, true.
So.
Okay, good point. I don't know if there is any other expert want to make a comment. Otherwise, we'll stop here. I can't see any other comments in both chats. So thanks so much, Thomas. It was very, very nice discussion.
So normally we would now go for dinner.
Yeah, exactly. That's the pity of the webinar. I mean, it's very difficult to do and let's say online dinner together. That's not so nice. But anyway, so thanks a lot, and thanks everybody.
Thanks for all your questions. Enjoyed being with you. Good to see old friends. Great, thank you.
Thank you.